Hi, welcome to the Calculus 1 lecture series. And this is the lecture number 6. We are still in the unit number 1, limit and derivatives. And we spent the previous 5 lectures and talk about the limits and how to find the limits law, all these things. And those are the foundation work before we introduce the derivative. So in the lecture number 6, in this lecture, we're finally going to start to use the limits definition and to define what is the derivatives here. And this is going to be a little bit a long lecture, so I'm going to divide it into 2 videos here. Okay, so the first video, we're going to talk about how do we define the slope of tangent lines. And then the second video, we're going to formally define what is the derivative by using the limit definitions here. All right, so let's go ahead and go to our worksheets here, the lecture notes here. Okay, so let's go ahead and start it, okay? So the first things here, we want to define the slope of a tangent line when the x equal to a special value a here. All right, so now in order to do this, let me try to do a graph here. So maybe I think that would be easier for people to understand that. Okay, so here, this is my function, let's say here. Okay, so this is my f of x functions here. Okay, so now the x equal to a, that means in here, this is my x-axis, this is my y-axis, correct? So when the x equal to a is in here, that means this point here, that means I'm going to find, so for this point, I'm going to find the tangent lines here, right? So this will be my tangent line, the green ones here. So we know from the geometry, the tangent line is a line only touch the graph at 1 point, correct? Okay, so I'm going to find, so my mission here is trying to find the slope of this green line. But also we know, from the geometry, in order to find the slope, how many points I need to have? I need to have 2 points, right? So we have like x1, y1, x2, y2. Then the slope formula, we say it's rise over runs, right? So how do we do that? We say, hey, it's y2 minus y1, x2 minus x1, right? That's what we all know from our algebra stage, from the time we learned algebra. Right now, we have this tangent line. It only touched the graph at 1 point, right? A. So how do I do that? So we say, okay, we have a in here we have 2 different ways to define it. So let me see here. So let's say here, how about I just choose any other general forms. Here's x here. Okay, so now for this point, when x equal to a, what do we come out here? We have f of what? F of a, right? So when the x equal to the any value x here, so what do we come out here? We have f of x, correct? So in here, we do have 2 points right now. And if you connect this point, right, the x and the f of a, so let me color coding that. So if you connect these 2 points, oops, right, so these red ones here, you still remember what type of line we called? This is what we call it is the secant lines, right? So it's touched 2 points here. So as you can see, when the x here getting closer and closer to a, what happens here? So if your x is moved over to here, let's see here, if your x is moved to here, right? So if your x move to here, so you have here, then you connect it here, right? So you will say, hey, this black line I connect with and the x here, it's getting pretty close to my green lines here. So I know when the secant line, the concept that we had before, so it's just when the x getting closer and closer to a, my secant line will become very close to my tangent line. So now let's take a look. How do I find the slope of my secant line? The second line, I have 2 points, right? So I have x, f of x, a, f of a. So y2 minus y1. So I have x, f of x minus f of a, then x minus a is here, right? So let me color coding that. So this will be what? This is the slope of what lines here? The red ones, right? So it's the slope of the second line, okay? So this is the slope of the second line here. And we also know, you know, when the x here, right, moving closer and closer to the A, then this red line going to get closer and closer to what? To the green line, the tangent lines, right? So I know the limit here when the x approach to A. So what is this one going to approach to? Because this is the slope of the second line here. So when the x approach to A, what is this limit going to approach to? This going to approach to the limit. So what is this limit here? This is the slope for what? This is the slope of the tangent lines here. Right? So this is the slope of the tangent line. So this is where the limit come to place, right? So we spend like the 5 lecture talk about the limit. This is where the limits come to play. So when you push this line getting closer and closer, so this red line going to gradually become this green lines here. So that's why the slope of the tangent line is the limit when the x approach to A, when the x getting closer and closer to A, right? Okay, so I have another definition. So these two definitions, different people, they have different preferences. So let's take a look. How do I write another definitions here? Okay, so here, this is my graph again, right? So this is my f of x here. And then now let's say here, I have A here. Okay, so I have A. So this is f of A. So I have what? This is my tangent lines here, right? So this green one, this is my tangent lines here. Okay, now I'm going to find, instead of find the x here, so what I find here, I say, hey, this point here, I call this A plus H, right? So that means this distance here, I just add what? This is what do I call this? The H's, right? This yellow part is the H. I just added the H's here. So for this part here, now I can have another points here. And just like we did before, if you connect these 2 points, what happens here? So this red one will give you what? This red one will give you the second lines, right? So if when you connect the 2 points, you get a second line. And then for this second line here, I have this point to give me f of A. So what is this point to give me? F of what? A plus H, right? So for the second one, I also can find the slope of the second lines here. So what is the slope of the second line? So it's A plus H, y2 minus y1. Right, so this is y2, this is y1. y2 minus y1, x2 minus x1. So it's a plus h minus x1 is a. So then here, this will be f of a plus h minus f of a to the h, right? So let me color coding that. So still, because this is the 2 points, so this is tell me this is the slope of the second lines here, right? Okay, and then the same way, I know, you know, in here, in order to become the, you know, in order to become the red line, become the green line, that means what happened to my H here? My H will become to what? Again, smaller and smaller. That means these 2 points are going to get closer and closer. So H will approach to what? Will approach to zeros, right? So now I can take a limit here. I can say limit H approach to 0. That means when the H gets smaller and smaller, then this second line will become closer and closer to the tangent lines here, right? So this one here is limit H approach to 0. So this is the end here, right? So this is another definitions about, so this way is here, this is the slope of the tangent lines here, right? You see my color codings here? Okay, so that's why you can use either one to find the slope of the tangent line. They have the, different people, they have the different, the preference. And then, in fact, this one's here later, this formula here later, when we try to find the general definition of derivatives, we will prefer to use the second one. It's easier to do and to get the general form or formula for your derivatives here. Okay, so now let's take a look at some examples here. All right, so here the first example say find the slope of the tangent line when x equal to 3. That means you want to find the tangent line when the x equal to 3. That means a equal to 3, right? Okay, so now let's take a look by using the first formulas here. So the step number 1, right? So you want to find f of a. So it's f of the 3. So this is 9 plus 6 equal to 15. You just plug in, right? Okay, so now the step number 2 is here. You want to find the f of x minus f of the 3, then x minus 3 is here. Okay, and then now in here, I have x squared plus 2x minus 3, right? Then this is x minus 3, correct? And now the step number 3 is to take a limit. And the x approach to 3, then this is x squared plus 2x minus 3, x minus 3. Oh, I'm sorry. So this is minus 15. So this is, I don't know where I got a minus 3 here. So not careful. Okay, so this is a minus 15 minus f of a, right? So minus 15. So if you put the 3 in the top and the bottom, you will get a 0 over 0. So we deal with this type of problem when we did the limit. So we say, okay, this one so we cannot do. So what do we need to do here? We say, hey, let's take a look. Will we be able to factor or not? So this one will give me x minus 3, x plus what? Plus 5. Then this is x minus 3. Oh, good news, right? So x minus 3 cancel out. So what is here is 8. So that's why I can conclude that the slope of the tangent line when they touch the x equal to 3 is 8. Okay? Okay, so now the problem number 2 is here. Let's say, hey, let's try to find the limit, the slope of the tangent line when the f of x equal to the 1 over x minus 1, a is equal to 2. So let's do the same way. The step number 1, what is f of a? See here, f of a is 2 minus 1. So this is 1 over 1 is 1. Then then we also need to find the f of the a plus h, right? So this is f of the 2 plus h. And here this is 2 plus h minus 1. What do we have here is h plus 1. Okay, good job. So then the next one here, I'm using the definition. So this is f of a plus h minus f of a over h. That's our definition. So now I can see here, f of h, this is h plus 1 minus 1 to the h. Oh, we did this before. So we say, okay, the way we do before is say, hey, let's try to find a common denominator. So this is h plus 1, and the common denominator is h plus 1. So then here, this is h, then this is h plus 1. So this is 1 minus h minus 1. Be careful, this 1 minus need to carry to both, right? So I got here is negative h plus 1 to the h. Then simplify that. So this is h plus 1 times 1 over h. And what happened? Boom, boom, cancel. So that's good. And so I will have the negative 1, h plus 1. Now the last step here is the limit. Take the h approach to zeros, right? So the f of a plus h minus f of a to the h will just be limit h approach to 0, -1, h plus 1. So what is here? So this will be -1 here, right? So that means the slope of this function at 2 is equal to the -1. Okay, now let's take a look. The next ones here, we did a lot of those practices here, right? So the next ones here, this one say f of g of x equal to 4x plus 3. Find the slope of the tangent line at a equal to 2. Okay, so let's use the first definitions here, right? Okay, so doesn't matter which definition. Let's say the GA. So that means 4 times 2 plus 3 is equal to what? Is equal to 11 here, all right? Then the step number 2, let's say the gx minus GA, x minus 8. So let's use the first definition. So the gx here is 4x plus 3 minus 11. Then this is x minus what? Minus 2. So this will be 4x minus 8, x minus 2. Okay, now let's take a look at the number 3 here, the limit x approach to 2, right? So it's the same old, right? So this is 4x minus 8, x minus 2. Oh boy, when you take the 2 in there, what happened here? You're going to get a 0 over 0. We say, oh, that's not good. Okay, so let's see. From the limit we learn, maybe I can factor and maybe I can simplify it. And say, okay, let's take a look at x minus 2, x minus 2. Oh, good job. I get the x minus 2 and x minus 2 cancel out. And so, and the limit to a constant. So what it will be? 4, right? Okay, so that's why. Okay, so we know this one's here, this is the limit of the tangent lines here, right? So this is the slope of the tangent lines here. As you can see, 4 is the same slope here because this is like, if in the algebra we call it, this is mx plus b. This is the slope for these lines here. Okay, so that's why they say, what is the slope of the tangent line to G at any points here, right? So that's what we say, okay, so because this is slope of tangent lines equal to here, so basically we said that because of the gx equal to the 4x plus 3 is a linear function, right? So this is a linear function. Okay, so now, so the tangent line to G at the A and the GA will be what? Will be the line itself. Okay, so which is what? Which the slope is 4. Okay, so I know because of that, because the this is the slope, right? So this is the linear function, so it's 4x plus 3. So that's why we said that the slope of the tangent line every place, everywhere, because these lines here is something like that. So every point is always have the slope equal to 4. Okay, okay. So now, based on this slope, and so let's take a look. What is the average rate of the change? So the average rate of the change is very similar like we did before. So the average rate of the change for the y equal to the f of x, okay, over the interval ax here. Okay, so this is just like we defined our, the slope of the second lines here. So the average rate of the changes here is just what? Is just like we said f of x minus f of the a, x minus a here, right? So that's what we call is the average rate of the change. So it's kind of like a makes sense, right? So you f of x minus f of a, what is the distance over the x minus a? Then the next thing is here, this is very important. We said the instantaneous rate of the changes here, all right? So the way we define the instantaneous rate of the change of y equal to f of x at the x equal to a at that specific moments here, okay? So we say this one here, this is how do we define it? That means it's x approach to a, okay? So this is x minus a, f of x minus f of a here. So that's what we say is the average rate. This is the instantaneous rate of change. It's kind of like we said, this is the slope of that tangent line at that moment here. So then the same idea, those things we applied a lot in physics. So in terms of the average velocities here, is really you just replace this with the time intervals, right? So now you only have, so instead of it, so the a to x, this is what we call is a time interval to the a to the x here, okay? So in here, so the average velocity is just like we did before. So this is f of a minus f of x minus a here. Then the very important here, instantaneous velocity at any specific moment at a instantaneous velocity of y equal to f of x at x equal to a. What will be here is limit x approach to a, f of x minus f of a, x minus a. All right, so that's one of the applications we use a lot for the, in the physics, we call it instantaneous rate of velocity. That's at a certain point. That means from that point, if you find the slope of that tangent lines here. Okay, so now let's take a look here. We said a particle moving along a scale in such that in the time t, this is their position functions here. Now I want to find the average velocities, right? So over the interval 1/4. So what is the average velocity? So this is the positions, right? So the average velocity. So the first one, when they start, f of 1, right? So you put it 1 here. What is it here? So it's 3 meters. So this is at a second and once the time, they did not say it's minutes or what. So when t is equal to 1, and this is the position it at 3. Okay, so now the same way when the t is equal to 4, I'm working on this intervals here, right? So the t is equal to the 4, so you plug the 4 in there, you will get this is like a 96 minus 16 plus 1. So this one will give you 81. All right, so the average rate of change, that means after, you started 1 second, you are at the position 3. So, right, so you are in the position 3, right? So this is 3 meters from the origin. Then after 4 seconds, you are at the position 81. So how fast do you go? You go to 81 minus 3. You travel the 78 meters, right? So this is my meters in how many seconds? 3 seconds. So what is in here you have here? So that means your average is 26 meter per second, right? Okay, so the same way you can do the other 3. So like this is like a f of 1. So the second, so like the second intervals here. So you would just say here, this is f of the 2 minus f of the 1 at 2 minus 1. So if you plug in, you will say this is 14 meters per second. Then the other ones here, you can say the f of 1.12 minus f of 1. Then here, this is 1.12 minus 1. And you can see here, this one, you put into your calculator, this will be the 9.2 meter per second. Now the last intervals here, you are travel only 0.1 seconds. Let's see here. So that means you have f of 1.01 minus f of 1. Then this is 1.01 minus 1. And you will get something very close to the 8.06 meter per second. So that means that when my times right here is this intervals here. If you take a look, right, this interval, the h equal to what? This is h equal to 3. This h equal to 1. This h equal to 0.2. This h equal to what? 0.01. So as you see, when the h get closer and closer, you know, to the 0, then my, you know, my average velocity going to kind of come to some number. So from this one, then the part B is asked me, said, hey, find the instantaneous velocity at t equal to 1. So I expect it should be very close to 8.06 because of when the h equal to 0.01. So it's, you know, the average velocity is 8.06. So let's take a look at what happened. How do I get instantaneous velocity? Remember, the instantaneous is the one you find the limit, right? So first I will say f of t minus f of the 1. Okay, so then this is t minus 1. So f of t is 6t squared minus 4t plus 1. When t equal to 1 is 3, so it's minus 3 here. This is t minus 1. So what is here? So this is 6t squared minus 4t minus 2. So this is t minus 1. Okay, so now let's say here when the t getting closer and closer to 1, let's see what happens. So this is 6t squared minus 4t minus 2t minus 1. Oh boy. So if you put a t equal to 1, you get 0 over zeros, right? So we learned from previous, so what you can do? Let's take a factor. So this one, I can factor out like a 6t plus 2, t minus 1, t minus 1. Then you say, oh, good. T minus 1 can cancel. So I'm going to have what is here? This is the limit t approach to 1. I'm sorry. So here's t approach to 1. Then this is a 6t plus 2. So what is here? So it's 8. All right. So you see here is a very, very, so when your h is 0.01, is already very, very close to your instantaneous velocities, right? Okay. So that's one of the very, you know, very, very common application in the physics. We talk about the average velocity and the instantaneous velocity. So basically it's the same like to find the slope of the tangent lines here. Okay, so let's do a last example, then we will stop here and we're going to talk about the derivative in our next videos here. Okay, so here, this one's here to say, you know, Fred is driving along the highway. At 3 o'clock, he passes the mile mark is 120 and the phi is 250, okay? What is his average velocity? Okay, so 3 o'clock to 5 o'clock, how many hours? 2 hours, right? It kind of makes sense. So at 3 o'clock is 120 miles mark. And now at 5 is 250. So over these 2 hours, how many miles how many miles the Fred drove here? 100 what? 130 miles, right? So now so this is 65 miles per hours, right? Okay, so now the second question is said, hey, when the Fred passes mile mark 162, is the speedometer showing 54 miles per hour? What is the 54 represents here? So we know that at this specific moment, 162, the mile markers layers, right? So this 54 is what? Is his is flat, so what is instantaneous, right? So it's flat instantaneous velocity. Okay, so let me say at that moment when he passed the 162 miles markers there, that's his car. If he look at his speedometer, his car showing he's doing like 54 miles per hour. Okay, all right, that's it. And we're going to stop the videos here. Then our next video, we will start by define the derivative finally, right? After almost like 6 lectures, we finally be able to start to define what is the derivative of functions here. Okay, that's it. Okay, so nice to talk to you and looking forward to talk to you in our next videos. Okay, bye.